Hi everyone, my name is Matthew Watson. I'm a senior robotics engineer at Opteran Technologies. Opteran is a spin-out company from the University of Sheffield, and we're commercialising £6 million of grant funding and 8 years of research into how brains solve autonomy and how we can use them to build better autonomous machines. You also might have seen us in the news recently, as just this week we've closed our seed funding round, so we raised 2.1 million to continue this effort. So I want to first lay out our vision. So in the 1940s, IBM's president apparently said that the world market for computers would be 5. Now, computers are embedded into the very fabric of our lives. They're running everything from watches to cars. Many are so deeply integrated that we are now unaware of their presence. It is said that we live in the age of ubiquitous compute. So the same can be said for the natural world. All around us, insects ply their trade, pollinating orchards, maintaining their colonies, and generally surviving. Most of the time, they go unnoticed by us, quietly solving their problems while we go about our lives. Autonomy and intelligence promises the same vision for the future. That is, autonomous machines moving around diligently, making the streets clean, keeping services running smoothly, and making lives safer. Ubiquitous autonomy is the next revolution, not just for industry, but for every part of human life. So, Opteran replicates and improves the algorithms that make these natural systems so robust and successful to create the autonomy that can bring about this future. We're not the first to target autonomy, but our approach is radically different. That is, we aim to replicate working systems for autonomy and intelligence from nature, not to create artificial intelligence that replicates none of the sophistication and efficiency of real brains. So at Opteran, we capture biological algorithms and we implement them in silicon. The research that has brought us to where we are today started when cognitive neuroscientists first started to map the human brain. We had a reaction to this and said, why would you start with something so complex? Instead of trying to map the 86 billion neurons in the human brain and then hoping that you'll be able to even understand this map, why not start with something smaller? So we chose the honeybee, as it possesses the ability to solve really complex navigational problems while using only 1 million neurons. And that is just what we've done. We've understood how this real brain functions, and we've re-engineered this into a silicon chip, the Opteran brain. And this can then be deployed at the edge to provide true autonomy in drones, robotics, and vehicles. So this lets us create autonomous machines that can move with the same robustness and efficiency as their natural counterparts. So what can a honeybee's brain do? What algorithms have we captured? So first of all, it is capable of stable flight control and collision avoidance in really diverse conditions and environments, achieved using only passive sensing. This requires the bee to understand its movement in the world, how to move based on this information to avoid collisions, and how to move to enhance the quality of its perception. Anyone who has tried to build an autonomous collision-avoiding drone will know that this is a challenging task, and yet insects make it look so easy. This brain is capable of 3D topological mapping. That is, it is able to learn a relative map of its world, from which it can then locate itself and then navigate over distances of several kilometers. And it's capable of decision making. So through instinct, this brain is able to plan its activities to perform useful work whilst meeting and adapting to varying complex real-world constraints such as energy reserves and availability, weather conditions, and threats. So again, all of this is achieved using 100,000 times fewer neurons than a human and in a brain only the size of a pinhead. So what benefits does natural intelligence bring? So these algorithms are highly adaptable in that they are general solutions for a given type of task. meaning they don't require a vast new data set to retrain for use in a slightly different environment. This is because it is brain structure that encodes the key behaviors required to master a given type of task, and this structure is already optimized and fixed by evolution, with learning then built on top of this at the edge. These algorithms are verifiable, so we understand these algorithms that we're implementing, meaning this is a white box approach that is therefore open to safety verification by regulators. This approach brings great algorithmic efficiency. So in evolution, any non-beneficial compute or sensing is a significant disadvantage, and so is selected out. And so these solutions are already optimized for efficiency, yielding the minimum amount of compute required to solve a given type of problem. Brains are responsive. They don't come with a connection to the cloud. They are always deployed and learning at the edge. So this lets us build autonomous machines that aren't reliant on this reliable cloud connectivity and compute. And in the near term, the rollout of our algorithms isn't dependent on the success of 5G and it living up to all of the hype. And finally, through their algorithmic efficiency, through the use of passive sensing, and through the lack of any cloud infrastructure requirements, their implementations on a robot can be really small, super lightweight, and ultra low power. So what specific algorithms are we extracting, and how do they work together? So we're breaking down the brain's autonomy solution into modular components. This follows natural divisions in brain structure, and this allows the application of these algorithms across problems requiring different levels of autonomy. So first, we want to be able to see the world like a natural system, labeled as C in a product stack. So across the entire animal kingdom, we see that a lot of evolutionary effort is dedicated to stabilizing the field of view against rotation. In insects, this is in head movements and flight control. In humans, this is in eye movements. We find that this effort has a purpose, and it can greatly simplify later processing stages by ensuring that interesting parts of the visual field remain in the same location, and perhaps more importantly, by eliminating movement in the visual field that is due to rotational self-motion, as opposed to movement due to the world moving or ourselves moving through the world. So our approach to this problem is the first example of the important difference between the blind verbatim replication of the method, which would be just simulating the exact neural circuit and hoping to get the same output, versus understanding and then re-implementing the underlying algorithm. So while nature uses a mechanical solution, i.e. the neck or eye muscles, we've instead been able to devise a real-time electronic solution, adapting and improving upon the underlying algorithm in relation to our available toolset. So C fuses multiple cameras to provide a 360-degree field of view, that is, we can see in every direction at once, and which is completely invariant in self-rotation. This means that the field of view remains identical as your agent or drone, for example, tumbles in place. On top of this, we also see that in nature there exists a large variety in the types of light to which eyes are sensitive. For example, insects can see in UV, which makes sky background segmentation much simpler, and some can measure polarization, which you can use as a compass. So we fuse all these data sources together into a single holistic visual field. So next in our product stack is Sense, which is a low-level perception layer. So at the heart of Sense is our brain-derived optical flow algorithm. So optical flow, for those who haven't heard of it, is a measure of how things are moving in your visual field. And this is able to tell us a lot about how we should react to an object even before we know what it is. So our optical flow algorithm brings greater robustness, accuracy, and efficiency than all existing approaches. And thanks to this robustness and accuracy, it also lets us implement a highly accurate collision avoidance algorithm for very little extra cost. So I'll go through some examples and benchmark results shortly. So as a demonstration of this performance and efficiency, here our See and Sense products are implemented on a sub 250 gram drone running on a 3 gram compute stick and using less than half a watt of power. So this drone is autonomously flying itself while both controlling its velocity based on its perceived motion of the world and whilst avoiding collisions with obstacles. This is achieved using only a single monocular camera for perception, and so is not reliant on the heavy and power-hungry depth sensors, LiDARs, or their associated GPUs or processors that most autonomous drones use. And the only 3 inputs I'm giving to the drone are takeoff, fly forward without hitting anything, and 2 minutes later, land. So I think this is a groundbreaking demonstration of the effectiveness and potential in our approach to autonomy. So safe autonomous movement is the first step. Next, we need to be able to move with a purpose. So our next product, Direct, builds upon Flow's perception capabilities to allow an autonomous system to learn a map of its world, and then to use that map to navigate. So the process of map building and localization is typically referred to as SLAM, that is simultaneous location and mapping. Traditional SLAM pipelines function by finding things in the visual field that stand out, a process called feature extraction. These features could be a table corner or a light fitting, and then using the movement of these features between camera frames to estimate how the robot has likely moved. This approach can fail if too many things look alike, like in modular buildings, if things in the world are changing over time, like in natural environments such as forests, and can be very sensitive to dirt and damage to the camera, and struggles with fast movement where the features might move a large distance across the camera frame. The back end of a SLAM system, that is the part that converts these feature tracks into a self-motion estimate, is a large-scale global optimization problem, which is difficult to parallelize for implementation on low-powered hardware. So we have a radically new and different approach to SLAM, which is based on our class-leading Flow algorithm. So Flow works everywhere, and so our technology uses Flow to work out how it has moved, rather than by tracking features. We then encode panoramic information that varies little over time to learn different locations in the world and to place ourselves within it, and we then fuse these into a topological map. So this differs from traditional SLAM approaches, which typically produce a metric map, meaning the maps are encoded in Cartesian coordinates. But this isn't how brains work. Note how terrible humans are at estimating distances. And this is less information efficient, and most importantly, these metric maps aren't necessary for autonomous navigation. So to navigate, you only need to accurately understand map connectivity, i.e. a topological map, understand your movement through the map, for us using Flow, and then to be able to move in such a way to be able to move through the map safely. So for us, Direct gives us this robust sense of location, which we can then combine with the safe adaptive behavior Sense provides us, that I just demoed on the drone, to allow for safe navigation between destinations. Looking further ahead, we're also working on decision making, where again, current rule-based approaches can break down when unanticipated circumstances are encountered. So real brains don't do this. They are experts at evaluating different courses of action with different importances and choosing between them while gracefully managing conflicts and ensuring that the right action is taken given the context. So our solution is naturally brain-inspired. So Decide implements a universal action selection switch that is based on years of research into robust and optimal decision-making methods. So features include graceful management of competing actions when opportunities arise asynchronously, value-sensitive decision-making, and tunable speed-value trade-offs. So this action selection framework can also be integrated with reinforcement learning frameworks to allow for online policy learning. And then looking even further ahead, we want to reverse engineer more parts of the brain to allow robots to not only safely and robustly navigate the world, but to also interact with it in complex ways. So, taking a step back, as I said at the start of this presentation, we aren't the first to target autonomy. In fact, artificial intelligence has made significant inroads in this domain in the past 8 years. However, AI and the deep learning that it is typically now built around is running into limitations. So we've all been eagerly watching self-driving car development over the past decade. Like me, you may have noticed that full autonomous driving is always promised to be just around the corner, and every month someone new is rolling out a new self-driving trial. And yet the rate of improvement has dramatically slowed. Deep learning has been probably the key enabling technology that has got autonomous vehicles to where they are today. And we're also finding that the rate of improvement in deep learning has slowed, especially in the past few years. So we're specifically looking at supervised deep learning here. So supervised deep learning is where we use labeled training data to teach a neural network the relationship between the input data and some output label, with the aim that the network will learn how to predict the label for a new piece of input data. So for example, this could be learning how to draw a box around traffic lights in an image from 1 million labeled photos of traffic lights. A key enabler of supervised deep learning was from 2012 onward, a synchronized explosion in data availability, in processing infrastructure, both learning and inference, and labeling infrastructure. So state-of-the-art networks are now huge. They're trained on vast data sets. As an extreme example, GPT-3, which is a natural language processing network created by OpenAI, which is capable of writing very convincing text and even poetry, is trained using the entirety of Wikipedia, and yet this makes up only 3% of its total training data set. For the past 8 years, the computation required to train these state-of-the-art networks across all domains, including vision, has doubled every 3.5 months. We also find that power consumption grows linearly with model size. And so, for example, training Transformer, another state-of-the-art natural language processing network, had a training carbon footprint equal to the lifetime emissions of 5 cars. And then GPT-3 that I just mentioned is 100 times bigger again, and apparently cost $12 million just to train. And amusingly, when found to have a bug, the authors couldn't afford to retrain it. And this is just training. NVIDIA, who make the GPUs that power a lot of this, estimate that 90% of the lifetime power consumption of a net is in its use for inference, not in training. So we're finding that deep learning is becoming exponentially too expensive to pursue. We're also finding diminishing returns. So ResNet is a well-known computer vision model released in 2015. An improved iteration, ResNext, came out in 2017. This requires 35% more compute to train, but only achieved a 0.5% improvement in accuracy. So we should note this is all in such stark contrast to an insect, with which its tiny brain can learn to recognize an object from fewer than 10 examples, or even in a human, in how we don't have to consume the entirety of Wikipedia just to learn how to write. Then, when we come to deploy these deep networks on our autonomous machines, we find that the high computational cost of inference for deep learning makes it challenging to implement these large state-of-the-art nets at the edge, and absolutely impossible to train them. So instead, we either have to shrink these nets and accept a hit to our performance, or we have to rely on cloud infrastructure to offload the computation, which creates a dependency on network connectivity and ongoing operational costs. Inference at the edge, while it can be done, requires large amounts of power and weight and brings high equipment cost. And this is just inference again. Meaningful learning at the edge is currently all but impossible. And this prevents an autonomous system from adapting to and learning its own unique operational environment. Training a new net is reliant on the availability of a suitable data set, normally specific for your application. So you find that the economic muscle behind autonomous vehicles means that acquiring a large labeled self-driving data set is now relatively straightforward. But what about other applications? So interestingly, dataset availability, curation, and labeling ranked as the top development bottlenecks in the Embedded AI and Vision Alliance's 2020 developer survey, with over 90% of respondents saying that there didn't already exist a suitable dataset for their target application. And this dataset dependence also creates a weakness in that if your training is entirely reliant on this dataset, then you are vulnerable to edge cases. That is, scenarios that are not encountered in your training data because you don't have enough of it or you didn't anticipate all circumstances. And you will often find that while you hope your optimized net will have generalized enough to handle this new data, for these edge cases you can't. Finally, deep learning is a black box approach. So answering the question, what is this trained network doing, is an entire field of research, and yet deep networks are still almost impossible to verify. This is a problem for regulators who have to ensure that these systems are safe. So fundamentally, we find that deep learning is just sophisticated statistical pattern matching. It is not a brain. So how does deep learning compare to Opteran's natural intelligence? So let's first look at the structural differences. So real brains are structurally very complex. Neurons come in many different forms, they do many different things and connect in a huge variety of ways. So complexity can be seen as hard to understand, and so deep learning throws it all away and creates something that can learn but does not work like a whole brain. So evolution has spent billions of years refining this complexity. So this complexity is not random, but it is structured to help solve real-world problems. If you can reproduce the complexity of the brain, it becomes easier to interpret and learn about the world. And we see that real brains solve many problems without learning and can rapidly learn to solve new problems. And performance-wise, as an example, let's look at a benchmarked comparison of our optical flow algorithm versus the deep learning approach. So FlowNet, I think these results are FlowNet 2 actually, is a deep learning based optical flow estimator, and Flow is our own brain derived algorithm. So we find we're able to achieve twice the accuracy 400 times faster. And furthermore, while FlowNet is best suited to GPU implementation because it's quite large, we can implement our flow algorithm on an FPGA using a tiny amount of resources. And this yields a further order of magnitude improvement in performance. Then again, let's quickly compare the system overview. So again, a natural autonomous system at the bottom doesn't use the heavy, power-hungry and expensive active sensors such as radar, LiDAR, and their associated compute. And instead, we see animals achieve great degrees of autonomy using just passive cameras. And again, where current AI systems are always having to gather huge amounts of data up into the cloud, where it's curated, annotated, and used for training, or even offloading all inference to the cloud, we deploy at the edge, which gets rid of this entire dataset dependence, and even doing our learning at the edge. So these system differences, again, all sum to yield lower power consumption, greater reliability, and perhaps most importantly, lower upfront and operational cost. So how do we do it? How do we go about reverse engineering a brain? So when reverse engineering, the most important factor is knowledge. So this is not an easy task. A brain circuit is a complex dynamical system that operates across multiple different time scales and is made of many very different biological components, all interlocking to cause a given behavior in an animal. So the first important form of knowledge is being able to describe a specific behavior. So the best experiments will test a behavior that only uses a small set of brain circuits, which makes experiment design critical. So we use sophisticated techniques, including virtual reality to control what the brain can see, omnidirectional treadmills to control how the brain thinks it's moving, and even harmonic radar to track how these insects move over long distances. And the second form of knowledge is working out the brain circuitry that produces this behavior. So this is the how neurons are connected. So this can be found by injecting dye into neurons or by genetic marking, and then slicing the brain and tracing the dye. And the third form of knowledge is we then need to know how these brain circuits function. So this is important, as depending on how the neurons in the circuit operate, the same circuit can produce very different behaviors. So this can be found by inactivating circuits to see if the behavior disappears by genetics or chemicals, or by recording the activity of the neurons while the behavior is performed, either using electrodes or again through genetic manipulation and imaging. And then the final step, the hardest part potentially, is to bring all of this knowledge together and to reason and work out what the underlying natural algorithm is, and then to create an efficient way of putting that algorithm onto a silicon chip. So Opteran's team is very diverse. I myself am from a control engineering electronic background, but we have a number of computational neuroscientists in the team. So we have a huge a diverse array of experience and many years of experience of doing just this. So finally, I want to talk about our deployment and integration pathway, how we work with our customers. So our development process allows for great flexibility in how our customers deploy our algorithms. So the way we develop is, first, we use a bespoke neural description language to define how these algorithms are implemented neurally. And we then use code generation to turn this neural description into an efficient algorithm implementation that could be targeting radically different compute architectures. So this could be GPU, FPGA, or even direct implementation in silicon. These can then be implemented for a specific vendor's devices. So for example, Xilinx FPGAs or NVIDIA GPUs. And then finally, through our libraries and tools, so for example, ROS integration, these can be integrated into an autonomous system. So depending on the customer's needs and volume, we can deliver solutions from any point in this process, all the way from bespoke algorithm implementations for unique hardware through to plug-and-play off-the-shelf solutions. And remember as well, these algorithms are highly general solutions for a given type of task, meaning they're suitable for application across a huge variety of domains. So we can target UAVs of all sizes, autonomous mobile robots, it could be in warehouses or factories, personal service robotics, in the home and office, off-world robotics, where our robustness and low power consumption really comes into its own, underground, or even underground or underwater, such as in mining or offshore asset inspection. And so to provide a quick path to testing and deploying these algorithms, we've created an Opteran Dev Kit. So this uses 2 cameras and an IMU for perception, and implements C to create a stabilized omnidirectional view, which is running on a Xilinx Zinc FPGA. This is currently running then Opteran Sense, which allows for immediate use for safe navigation and collision avoidance. And we will soon be updating this to implement Opteran's Direct product, which will provide a standalone plug-and-play SLAM solution. This is easily interfaced via gigabit Ethernet, typically using either our driver library or our ROS node, and draws 3 watts from a 5-volt supply. While this image here is the base PCB, it is shipped as a assembled unit, which comes with 2 fisheye cameras with opposing fields of view, but can be adapted to your own camera placement. And thanks to the programmable nature of the FPGA, we're constantly continuing to add features and enhance our products on this device. And then once prototyped, the algorithms can be moved to ASIC or CMOS implementations for lower cost, large scale deployment. So thank you for listening. I hope you can see the same potential in natural intelligence as we do. And I hope you will join me in helping to advance the world toward this vision of ubiquitous autonomy. We're always hiring, so please don't hesitate to get in touch. Here are my contact details, and that for our CEO are at the bottom of this last slide. Again, thank you for listening.
Welcome back. First, I'd like to thank Matthew for his presentation, and I speak on behalf of Brez, and I hope most of the audience when I say, wow, that's some incredible stuff you're doing there, and we really appreciate you coming out and presenting it to us. So we've got a few questions of our own to ask, and then we've got some from the chat. My first question was, how do you find a balance between adapting the natural qualities that you find in research to the electronic and robotic components, and then actually developing more efficient methods of doing that using those robotics?
So about striking the balance between, so if you mean striking a balance between exactly copying what a natural brain would do and what we need for robotics, I think that's just where experience comes in. I think we're trying to be quite market driven, so we're not replicating algorithms for the sake of it. We're replicating useful algorithms that we can apply to a robot and then imbue it with the types of autonomy that we need. So yeah, I'd say judgment comes into a lot of it, and we generally try and evaluate our own work by real world demos. So it's not done until it's successfully completed the real world task, whether that's successfully navigating a building or whatever your demo could be.
Fantastic. No, very, very fascinating stuff. Another question I've got here is, what are some of the most unexpected discoveries you made in your research in comparing the natural brains and natural sciences to what we have in robotics fields and AI fields?
I think the best discoveries are just realizing the importance of some of the simplifications we see in the natural world. So realizing what a difference you can make by just stabilizing your field of view. That was quite a significant discovery. And then we also found that this work fed back into the neural understanding as well. So, for example, for the optical flow algorithm, looking at the brain, we had data going in, we had the data coming out, but we didn't quite know what the brain was doing.
Okay.
So then going through this process, we understood what the brain was doing, and suddenly we filled in our biological understanding as well. So that was a nice surprise.
Brilliant. I'm actually so interested in this. More on specifically the Bebot that you showed. Is that cool for me to call it that?
Yeah.
How much data is that actually processing, or should I say how little data it's processing? Because it seems like you've made it so efficient. I was just curious as to how much is actually being processed there.
Yeah, sure. So the camera it's using was, I think it was a 640 by 480 resolution image. That's then it's looking at a mirror, so it can see in all directions.
Yeah.
We then chopped that down to, it's about, I think it was 64 by 128 pixels. Because yeah, while lots of robots get equipped with 1080p 4K cameras, we see in nature that insects especially can achieve incredible flight using actually quite low low resolution imaging, and that's just what we do. So we process that low resolution image at about 90 frames a second, and that's more than enough for achieving that level of autonomy.
I'm actually blown away by all of this. One question that I think came from the chat was where, oh no, this was actually me. Sorry. Where do you see this sort of type of AI taking place in the world? Do you see this taking over AI as a field entirely, or do you think that there will always be a place for conventional AI and this is almost something completely different?
So I'd say that conventional AI is very good if what you need is pattern matching. So I can see that holding on to like the object classification area for a while, and things like you could Google search, for example. But as I discussed in the talk, it's really running into limitations now, and just doesn't translate well for some of the more physical autonomy tasks we want our robots to achieve, like the mapping, like navigation. So yeah, we see this approach of understanding how brains have already solved these problems as hopefully taking over.
That's actually leads into my next question quite well. Would you say your limitations at the moment, are they more based on the technology that you have access to, or more based on the data that you're researching?
Our limitations, I'd say we can move as quick as we're able to reverse engineer these algorithms. So yeah, as I said at the start, we recently just closed our seed round. So right now the limitation is getting manpower in.
Yeah.
So if you're interested, get in touch. But yeah, we generally find that we can find ways of turning these complex neural algorithms into something we can put on silicon. So far, we've not really run into hardware limitations. In fact, we find the hardware is plenty powerful enough because it's been designed, a lot of it, around the brute force approach. So we can now use a fraction of that, and it's enough for us.
Fascinating stuff. One question that came from the chat as well was energy consumption is a huge hurdle for the automotive industry, automotive autonomy. What challenges do you foresee with implementing your solution in the automotive industry?
I'd say I think the main challenge is traction. Simply, these are huge players in this field, and we need to catch up and convince everyone of our approach. But I think it's doable. We are starting to see some of the main players are struggling. I think Uber have put their autonomous driving division up for sale. Wow. Last I checked. So yeah, I think in the next few years, as this automotive investment stops giving the returns people hoped it did, then people might start looking for the alternative, and we'll be ready.
Well, on that note, we had a question from the chat, which I'm also quite interested in, is what roles are you hiring for?
So right now we've got a software engineer position open. Okay. As I say, we literally closed our funding round the start of this week, so we'll have more coming soon. And yeah, we're trying to build the team across all the way from neuroscience through to the engineering side and even the business side as well.
Fascinating stuff. We've got a minute or two. Just more on the bee. What? How did you? Because you said the vision of a bee is so much more limited than a 4K camera or something like that. How did you determine
that? Determine that metric, simply looking at a BI. It's a compound eye, so you can see each individual pixel in quotation marks. And yeah, I forget the exact number, but I think a dragonfly has maybe 100,000 of these, and I think a bee is about a quarter of that. But as I say, I'm a control engineer. Ask the neuroscientist, and they'll give you a better answer.
No worries at all. And just quite an important question, just maybe running over a minute. Beyond general obstacle avoidance, what is the core aim of your research? And what do you see this being utilized and developed towards in the future?
So we're trying to build capabilities. As I said, we started with being able to move safely, just like an insect can fly around a room without crashing most of the time. After that, it's the mapping and the localization, because then you suddenly have a robot that can go from A to B, and that has so many uses. Beyond that, then we want to bring in decision making and then interacting with the world. So we'd like to see these robots learning how to manipulate objects and make complex decisions.
Fascinating stuff. I will definitely be keeping an eye on your research. Thank you so very, very much for coming to speak to us. It's been a pleasure.